Okay, so we will just continue. We did the first two problems, right? So let's finish these up. So remember, the whole point of optimization was to make something as good as it can be, and a lot of times you can formulate this as making something as large as possible or as small as possible. And so we're really trying to find a systematic way to maximize or minimize something, and that method was optimization, which I gave you the steps for last time, and we're just going to do a few more examples to finish this section. Okay. So now we're doing problem 3. And this one actually comes with a diagram. Sometimes they actually give you one. So we have a rectangular corral, 162 square meters. It's to be fenced off and then divided by a fence into 2 sections, as shown in the figure. Find the dimensions so that the amount of fencing is minimized. Okay, how do we begin? Right, start labeling them, right? So you know, so I can say X is this whole thing, that's fine, Y is this whole thing. Which means that this side is also X. It also means that this is length Y and that is length Y. So we read the problem, this is our diagram, so now we have to come up with our objective and constraint equation. So, what is our constraint? 162 square meters. What does that mean? Area. Square units mean area, right? So the constraint is actually the area. The area is going to be 162, but the area that this covers is just x times y. So this is our constraint equation. What's the objective? Perimeter is going to be the objective. We want to minimize it. So we have 2x plus 3y is what we're going to want to minimize. So we covered steps 1 and 2. This was step 3. Step 4 was solve for one variable from your constraint and plug it into the objective. Which one do we want to solve for? Doesn't even matter, right? So let's solve for y. 162 over x. This means the perimeter now I can write as 2x plus 3. Well, now I feel like I should have solved for the x because now I'm going to have to multiply by 3 instead of 2. Do what you can to make your life easier. Okay, so what is this? What's 3 times 162? Do I even care? 486?
Yeah.
Am I following the steps? Okay, so now we're going to have to find absolute maximum. So we need to find the derivative, which is going to be 2 minus 486, that's the minus 2. For minimum p, set p prime equals 0. Or undefined, but undefined means x would be 0, which doesn't make sense in our setup, so we just move on to setting this equal to 0. I can multiply both sides by x squared. And so x would be the square root, which is what? Is that a nice number? Huh? square root of what? Is that a nice number? Well, what can we take out of that? We can take out a 3. That's 3 times what?
81.
81. We can take out, but 81 we can square. This is just 9, so it's not a completely nice number, but it's not bad. And so this would mean y would be 162 over 9 radical 3. Does 9 go into 162?
Yes, it does.
How many times? So now we are on step 6. So dimensions are 9 radical 3 by 18 over radical 3. Like I said, most of the time, if you only get 1, it's going to be the answer you want. You can always do a check. It'll set your mind at ease. Right, that 9 radical 3, you check it in the derivative. Right, so you can plug in a number over here, like 1, plug in a number above. 10 wouldn't be. We need something bigger.
15.5.
20 or whatever, it doesn't even matter. All right? So, and if you plug in something like 1 here, what did you get? You realize you get a negative, it's going down. Plug in something over here, you would get a positive, it's going up, and you end up with this being the minimum, which is what we wanted.
Professor, I don't understand why you put 3 y's like right here. Yeah, I understand 2 y's. Why did you put 3 y's? But why not just 2 y's?
Because all these lines represent parts of the fence. So this is actually a part of the fence.
Alright.
Alright, so I want to actually count that length as well.
Alright.
So we have this rectangular corral, but they broke it in 2 with another piece of fencing. So that has to be counted.
Alright.
Any questions?
Professor, what is the quicker way to, you see we have 9 radical 3.
Yeah.
Like, what is the quicker way to understand in a number, like in the decimal point?
Well, you'd estimate it. You know that radical 3 is somewhere between 1 and 2.
Radical 3.
Yeah, right? Because it's less than radical 4, which you know is 2. It's definitely bigger than radical 1, which is 1. So pick a random number between 1 and 2 and just estimate.
So it should be around 9.2 or something.
Yeah, so this will be something like 9 times 1.5. If you don't have a calculator, just think of it that way. Okay, 4. A cylindrical can without a top is to be made to hold 8,000 pi cubic meters of liquid. Find the dimensions of the can that will minimize the amount of material needed to make the can. That is, minimize the surface area. And as I put a note here, this was taken from a 205 final. If this were a 201 problem, they wouldn't give you that last sentence. You'd have to be able to figure out that they're talking about surface area.
205 is harder than 201?
Huh?
205 is harder than 201?
As far as optimization is concerned, they're both sort of the same. 201 is harder, technically speaking. So here, we read the problem. Step 2, diagram. We know it has an open top. Now we want to label the diagram. How would we label this cylinder? Well, the radius would be nice to know. Any other thing of importance? The height of the cylinder. Okay. By the way, so here they already told us we want to minimize the surface area. How would we get to the surface area of this can?
2 pi r times r. That's
What?
2 pi r times r plus h. Like 2 pi r squared plus 2 pi r.
How did you get that?
You open up the cylinder.
Yeah, the idea is you slice it, and then you unfold it. What you end up with is a rectangle. And we only have one circle now because the top, there is no top, right?
Yeah.
So here's where the height is. Now this length would be what's going around, so that's the circumference. So you know that's 2 pi r. This is just a circle of radius r. So the area of this is 2 pi r h. The area of this is pi r squared. This means total area 2 pi r h plus pi r squared, and this is actually your objective. You want to minimize this. What is the constraint? Volume is a constraint. How do I know it's volume? Because they gave you cubic units, right? These are things that you should be able to pick up on, right? If they just give you a unit of length, that's just a length. If they give you a unit of length squared, it's an area. If a unit of length cubed, it's a volume. So volume is going to be our constraint. What's the volume of this cylinder?
8,000 pi.
The formula.
Oh.
Pi squared.
Pi r squared h, and we know that that's 8,000 pi.
Yeah. You solve for variable.
Step 3. Solve for one variable here, plug it into there. So we can solve for someone here. Personally, I'd rather solve for the h to avoid square roots. So now I know pi r squared h is equal to 8,000 pi. This means that my h would be 8,000 over r squared. This also means that my area function can become this equals that. So I have 2 pi times 8,000 over r, or sorry, r to the minus 1. Step 4. Now we want to find the critical points of this guy. So a prime would be plus 2 pi r. For minimum a, set a prime equals 0. Because it's undefined, where r equals 0, which means we don't have a cylinder, so we ignore the undefined case. And so this means that minus 2 pi times 8,000 over r squared plus 2 pi r equals 0. I can divide both sides by 2 pi. I can also multiply by r squared. This would give me 8,000 plus r cubed minus. So this means r cubed is equal to 8,000. So r would be the cube root of 8,000. Which is going to be what? 20. And this is in meters. Meters. Yeah, it's a huge can. Okay. far, is this difficult? Is it
Yes.
like, you find this difficult?
Yes.
It's not good, man. I don't know.
Worse than related rates or better than them?
It's better than this sheet.
Huh? What?
I said beginning of the class, you just told ignorance.
This is the wrong one. That was curve sketching. Did you get the curve sketching one?
We have to close on 5.
I didn't get the curve sketching one.
You didn't get the curve sketching one?
Thank you.
Yeah.
Okay, let's move on. Where are we now? We are in so this was step 5. What I call these steps?
Yeah, that's not 5.
Step 4 happened over here.
Second half, second part, second portion.
Right here?
Yeah.
Okay, so now where are we? We know R equals 20. This means find the dimension. So we want to find the radius and the height. So we know the radius, so now we get to the height. We know that h is equal to 8.23 over r squared. Eight one two three over 400. So this is step 6. So each count, do they really need to write meters? Huh?
It's not square. I mean, it doesn't matter
For what?
for the area dimension.
No, these are just lengths. The radius is a
Oh, yeah,
length and the height is a length.
You add that.
Professor, wait, on the sketch, I was confused on how did you made it half? Did you cut it like half? How did you cut the rectangle? I was confused on that.
Oh, well, it's like if I have a can, I just slice it and then unfold it. It ends up being a rectangle. Where the length of the rectangle is just the distance around this circumference
Oh, I
of the
thought
can.
it was like this, right? You cut it half and it's like this. Now you have a
No,
rectangle.
no, it's just a can, so it's just, you get this. So, start, let's move on.
Wait, can someone else do the next one? No,
Someone
like
else?
when you incorporate us, you know what I mean?
Okay. Let's incorporate everyone. Number 5.
So nobody gets it, nobody's saying it. I get it. So do it. Yeah, but you have trouble with this problem, don't you? I said I'm catching up with what I so you don't get it, right? Yeah, I do get it. Okay, that's all paying attention like where it's happening right now.
Order in the courtroom.
All right, Ashley, show her that you can do it. Come on, tell me how to do number 5. Sure, go on. How would you do this?
So first, you would have to read the problem.
Read the problem. Good. Step 1, read the problem. Okay, The manager of a department store wants to build a 600-foot rectangular enclosure in the store's parking lot to display some equipment. 3 sides will be built of redwood fencing. The cost is $14 per running foot. The 4th side would be built of cement blocks. The cost is $28 per running foot. Find the dimensions of the enclosure that will minimize the cost. Okay, so we've read the question. Now what? Now we will draw a diagram. This is step 2. What's the diagram? Mm-hmm. 3 sides different from the 4th side, so maybe you might want to indicate that some way. So let's say, okay, good, all right. Now what?
After that, you define the objective. Oh, wait, we have to label it.
Okay, how would you label it? Were you told it was a square? Because if you call this x and that x, you're automatically assuming it's a square. So call this x, call that y. Okay? So now, how do we get these equations? Objective, that's right, and the constraint. What's the objective? What do we want to maximize or minimize here? Minimize what? The cost. Okay, so we know we want to minimize cost, so this equation is going to be the equation that describes the cost, right?
Yeah.
So if you want to say the cost is, what would you say based on this description?
The cost will be 2x plus 2y plus x.
2y plus x
Plus
But when you have to
I'm not sure how
multiply,
to say it, but the last side will be multiplied or
Multiply that by the cost, which is 14.
Right, you have to multiply this by 14, right? This is the length of these,
yeah.
but they charge you $14 per unit length. So that's
X.
plus 28 times x, right, which is just the length of this one. So that's your cost equation. So this is 28y plus 14x plus 28x, or 28y plus, at least what do you get? 42. The answer to life, the universe, and everything. What's the constraint?
2x plus 2y. 2x plus 2y.
Yeah. What is the constraint here?
X squared y equals 300.
X squared y equals 300. How would you get that?
So x plus 2y equals 600.
Oh, yeah.
2x plus 2y equals 600.
2x plus 2y equals 600. How did you figure that out?
Asking for perimeter cost
How do you know it's a perimeter?
because they're charging you.
Because it's not from a square or something?
Right, because the units that was mentioned is foot, right? Not foot squared, not foot cubed, so it's not a volume, it's not an area, it's a length, right? They're telling you the length around this is 600, right? So the length around that is 2x plus 2y, 600. Or this is just x plus y is 300. Okay, now what? Step 4.
solve for one variable.
Solve for someone here, plug it into the objective.
Minus 300 minus y. X equals 300 minus y.
No, y equals 200.
Yeah. Why better? Both Y's.
Y is better? Well, if you substitute the y, you're going to have to multiply that by 28, as opposed to substituting x, you have to multiply by 42. This is going to be the smallest guy, so we probably want to solve for the y. It doesn't matter, but it might make our lives a little easier.
After this is all easy. That's the hardest part, finding the constraint in the formula. That's the hardest part of the...
Yeah, these two are the hardest part. And now you would just have 28 times 300 minus x plus 42x. Yeah.
On the test, would you have numbers this large, or would you be allowing us to use some calculators for it?
There are no calculators.
So the numbers just going to be like 4 and like 3.
These are the questions
No.
final.
You have to know how to add.
The final questions.
Not
How am I
fair.
supposed to multiply 20 by 300?
You multiply 28 by 3 and then multiply that by 100. You just add 2 zeros.
No.
84.
So it's 28 by 300.
84.
What?
84.
84?
Yeah, 0, 0.
0, 0 minus 28x plus 42x. This gives you what?
I wanted 150 on purpose. Yeah, shit.
What is this?
14.
Huh?
14.
14?
He said 40.
Now what happens? That's a weird thing. So step 5, find the derivative. That's 14. That's strange.
Yeah, I think it's a mistake. I just can't find something.
Something went wrong.
No, that's right.
What?
No, that's right.
Well, it's right by following the problem, but
This is why you should have those numbers.
There's no value that minimizes the possible.
exactly. This means that, which means this is a stupid question. I guess there was a typo in the final. This poor kids, huh?
They failed this final.
No, they're like, I don't know what to do anymore. And they did this wrong and they bombed everything else. There are no critical points. Yeah. I've seen that happen about twice since I've been here. They just put a question that has, like, didn't make any sense.
Would that be a valid
So here, can't be done.
Done.
Yeah, that's not fair because the kid will
That poor department store will never open.
The department store will never be able to display the script.
You want Walmart.
So they would take this out, right?
They're supposed to take
Yeah, they probably corrected the typo in the rules or something. Or they probably cheated and just said, oh, consider this to be area, then you multiply the x by the y and you get something easier.
You know this.
That's probably, they probably wanted to encompass a 600 square foot area. That would work out, right? Because it would be x times y and it would be similar to
Because it's
y.
usually one of them is area, one of them is perimeter.
So this is another example of something that can't be done. You can't give me a perimeter and expect me to minimize something like this. It's just can't be done. There's no best way to do this. So just take your pick.
That was the purpose of this question. To show us what we can't. Yes.
So you're not all powerful.
To show us that sometimes there's situations that we can't do anything
Sometimes there's
easy.
nothing you can do. Just
Kind of like me in chemistry.
but I think if you said the 600 foot square area, it should work. Okay. Alright, let's stop. You guys can try the other two on your own. They're bonus problems.
Did you get brownies? Because the number 7.
You might get brownies. Divided by Rashard.
You thought I was baking
Rashard.
brownies?
What?
I
I can buy brownies instead of bake them.
Fine, if you want to. Rashard will buy you a brownie.
Hey, there was anything about that.
You just did. Okay.
What?
So we're going to move on. 3.6 we're going to skip. It's not in our syllabus. We're just going to move on to 3.7.
What's 3.7?
3.7 is something so cool.
Oh no. Don't tell me what I think it is.
You don't know what it is.
You want to switch?
Write it.
Huh?
Write it out.
Tell me what it is.
Yeah, I want to ask a question.
No, you can't do that. It's cool. Antiderivative. Antiderivative. Okay, so now we did calculus, we're going to do it backwards.
Yeah.
Now we go back home.
We don't need it here.
Professor, we're going back home.
Okay. Let me give you a definition. F is called an
My prayers have been answered.
So this is the definition of an antiderivative. It is just a function that when you differentiate it, you get some other function, right? So let me give you an example. Example, f of x equals x squared. Find an antiderivative. What's the antiderivative?
What?
2x.
No.
That's the derivative. Antiderivative.
X to the third over. X to one.
Oh yeah.
I don't know.
Is it like x plus
X to the third.
Yeah,
X to the third.
Yeah, x to the third over 3.
You add
3x to the 4th.
Plus c.
Oh yeah, plus c.
Yes, please.
Well, we did a 9 day, so we can do that.
Just like plus
I said antiderivative. Anyone, right? Why?
Does it go backwards when you
Since if you differentiate x cubed over 3, the answer would be 3x squared. You get x squared, right? Now, if we want the most general antiderivative, it would be, what would the antiderivative be?
In general?
Yes, the general antiderivative for this particular function.
X to the n.
Oh wait.
X to the n. X to the n.
X to the n plus 1 over n plus 1.
I don't know what you're talking about. X cubed over 3. Plus c. Why is this guy here?
Because it's constant.
Remember the video I put you in the library?
It's infinite. It's infinite.
There's a reason I play calculus
Right, because this, the c is just in case there was a constant here.
See? That's why I played calculus factory earlier.
It would disappear when we took the derivative, so we have to put it there. So for example, your f could have been x cubed over 3 plus 5, or it could have been x cubed over 3 plus pi. It doesn't matter, they would have both given you x squared as the derivative, right? So the fact that you could have a constant here means that when you get this answer and you want to go back, you have to put that plus c there, right? Because if there was a constant, you would know about it, he would disappear. So you always put this placeholder just in case there's a constant. There are times when you can figure out what that constant is, but you'll need additional information, right? So they have to tell you something else for you to be able to figure that out. So this leads us to a theorem. And this actually fits in nicely with a theorem we mentioned the last time where, I forgot what section that was in, 3.2 or something, where we said if we had two functions that have the same derivative, then one was the other plus a constant. This is sort of the theorem that you use to prove this. So this says if f of x is an antiderivative f of x, then f of x plus c is the general antiderivative. So you use the word general when you want to encompass all situations. And this is sort of bad of me, but we're going there anyway, so I don't want to keep us all in suspense. General antiderivative is also known as the integral. No, the definite integral is a particular antiderivative, it's not the general. Notation, which when we go into chapter 4, we're going to see it, would be f of x is equal to this little squiggly sign with f of x dx, called the integral of f with respect to x, which is again you're talking about the antiderivative. Anyone knows why you use that word symbol?
Yeah, it's a sum.
It's a sum. Sum of what?
Let's not go there.
Huh?
Some of little rectangles.
Sum of little rectangles is one way you can think about it. Right, it's the area underneath the function, which is given by the sum of rectangles, which we're going to call Riemann sums when we get to chapter 4. So it turns out that the reverse of the derivative, the reverse of finding the slope, is actually finding the area under a curve. Which is sort of weird when you think about it. And if it doesn't make sense, don't feel bad, because it took mankind over 2,000 years to figure this out. Okay? When Newton and Leibniz came along.
I thought when you do the antiderivative, you would go back to the function.
Yes, but it's equivalent to the area, right? So we'll talk about that. So basically for thousands of years, these were treated as two separate problems, right? People trying to find areas on the curves, people over here trying to find velocity and tangent lines. And we're doing this separately for thousands of years, and no one ever realized that they're actually two sides of the same coin until Newton and Leibniz came along. But that comes from the fundamental theorem of calculus, which we'll get to when we do chapter 4.
What was his name?
Isaac Newton, Gottfried Leibniz. Okay.
Yeah,
So,
ruining our GPA on 2 fronts.
Holy shit. So I can fly
In case the door is open.
sold by Zenji, which is also
That's your old thing.
Okay, so let's start this A. 1/4 x to the 4 plus c. Same thing. It's the same thing, yes.
Wait, how are you getting that? What?
He just magic what he did.
That's what I want you guys to figure out. How am I getting this? Now that I showed you, do you see why it works?
Yeah, a little bit.
If you differentiate it, you're going to take this power, you're going to bring it down, you're going to kill that 4, you're going to subtract 1 from the power. Right? Remember what we're doing is we're trying to reverse the derivative, right? So when you're taking a derivative, what you're doing to the power is you subtract 1, which means if you want to reverse it, you're going to end up adding 1 to the power. And then you have to worry about that power coming down, and you have to cancel it because then you have a 4 that wasn't there before. We're going to get to why it works soon. What is this one?
It's just 1/6 to the 6.
1/6 x to the 6. Plus c. Or x to the 6/6 plus c.
Let's say you're going
Because if I'm differentiating, I'd move this 6 down. So I put that 6 here to cancel it. I'd subtract 1 from the power to get x to the 5th.
You are finding the antiderivative, right?
I'm finding the antiderivative.
So you will not put that comma on the bottom?
What on the bottom?
You know, when you find the first derivative, right, you put the comma on top. Why don't you put the comma on the bottom?
The comma?
The comma thing.
I think he means a apostrophe.
Yeah, apostrophe.
Oh, well, no, this thing, if I put the apostrophe here, it's just giving me that function. I want to get away from that. What about 2x cubed?
I don't know.
2x to the 4 over 4.
Actually, 1/4 x to the 4.
It's x to the 4
Oh, yeah,
over 6.
X to the 4 over 2.
Over 2. 2 plus 1, 3.
1/2.
No.
1 over
Yeah,
yes, 2.
Wait.
Yeah, that's true.
Did you guys say I plus 1? So we can add 1.
Alright, so here's going to be the real. If f of x equals x to the n, x not equal 1. Well, doesn't have to be. We already proved that derivative doesn't need. You don't need to. Then. So what's the rule?
N plus 1.
X to the n plus 1 over n plus 1 plus c. Right? And remember, the point is we're trying to reverse the derivative. So, you know, if you're taking the derivative of x to the n, you have to realize what you actually did, right? First you took the n's down in front, then you subtracted 1 from the power, right? Now you just want to go the other way. You want to reverse this process, right? So here the n you can think of as the old power. So to actually here what we did was we multiplied by what the power was before, right? So if we want to undo that, we have to divide by it. Right? So it's probably better I just show it this one. I can replace all the n's with like n plus 1s. So I put this n plus 1 down here. And then I subtract 1 from the power. It'll probably look nicer with that one. So pretty much you're trying to reverse this. So instead of multiplying by n plus 1, what do? You divide by n plus 1 because you want to undo this change. Instead of subtracting 1 from the power, you add 1 to the power. Right? So instead of multiply, you divide. Instead of subtract 1, you add 1. You're just reversing the rule. So this means if I take the integral of x to the n, x, this gives us x to the n plus 1 over n plus 1 plus c, where n is not equal to minus 1. Why can't n not be minus 1?
Then you would divide by 0.
Then you divide by 0, which you know is unforgivable. Okay, moving on to the next one. This you have to know this rule, it's super important. We'll come back to it in chapter 4, but it's super important for you to know. So f of x is sine x. What is f, the antiderivative? Minus cosine x plus c, why? Because if you take the derivative of this, you get negative sine times this negative gives you back a positive sign. Derivative of the constant will be 0.
Do we have to memorize these all over again?
Yes, you're going to have to memorize these all over again. So this says the integral of sine x dx is actually equal to minus cosine x plus c. So for now what you can do is you just remember how you took the derivative and you're just trying to reverse the process, right?
What does that integral mean again?
This means antiderivative. The general antiderivative of sine x is this function.
So is it going to be like completely different stuff for the
It's going to be
trick?
very different.
No, for the trick stuff. You know the stuff we have to memorize for different?
Like what?
Like cosecant.
Yeah, to integrate cosecant and yeah, they're all going to have.
And also the rule of one.
Like most of them we won't do in this class because it will involve functions that we haven't done yet. For example, the integral of secant involves the logarithm, which we haven't done, so I can't.
You just have to find the derivative and antiderivative of cosine.
You see by that. And
That's what I'm saying. It wasn't
What do you think is
negative cosine.
No, like, yes.
what's the antiderivative? Sine. Why is it sine x? Because I have to differentiate this to get that. That's why.
Negative sign.
This tells you that the antiderivative of cosine x is
I don't know.
It's different from how much Professor, it's the same thing for the trigonometric functions, right? You either find antiderivative or derivative, it's the same thing.
It's not. One is the reverse of the other.
It's the same thing, right? Just the process is different.
It's not the same. The derivative of cosine is minus sine, which I was just going to mention. Rookie mistake with these guys is the students messing up the signs. Right? Derivative of cosine is minus sine.
I already messed up the sign with just derivative. This is
What?
I already messed up the sign with just derivative.
Oh, well, now you got to
That's the fundamental.
What about this one?
This is not fun.
No. I said this is the second fundamental thing of math overall.
Integration by parts is calculus.
I saw the video of that.
Integration by what?
Integration by parts.
Oh, can we not?
Integration by parts here.
Can we not? No, it's still even.
UV, SV.
Oh, we're going there.
We're not going there. Don't worry.
Thank God.
But we're going to be able to find a method to integrate things like this, but I just want to see, can you guys actually see what it
That's
is?
the inside first, then the outside.
Chain rule, right? So you see here the inside is an x squared. You know that, oh, well, if I did the chain rule, I'd have multiplied by 2x, and that would have put the x outside here. right? However, we would have put a 2x out there, but there's only 1x out here, so we know that there has to be a half here that will kill the 2. Then what?
Now with x.
How do I get to a sign?
Cosine.
No, negative cosine.
It has to come from a cosine, right? But it has to be negative because I know that derivative of cosine is minus sign, so I need to kill that negative. I multiply by 2x and this half out here is going to kill the 2. Right now, don't worry if you didn't see it right away. We're actually going to do a systematic method to do things like this. So this section is all about reversing the derivative, getting you used to the idea. And then we're going to find out methods of how we can do this with more complicated looking functions. Like I said, why we want to do this, there are a lot of applications to it that we will be seeing in the future. Now this actually helps us do a lot of things that we couldn't have done before. So for example, recall, remember when we said S was the position function? Position function. If we want to get to velocity, what did we do? We found the derivative of S. This is the velocity.
Yeah.
Right? And then if you want to get to acceleration, we find the derivative of the velocity function. Get acceleration. Now it turns out to actually move down, of course, is what we've been doing before. This is u differential. Now we know, at least conceptually, how we can go the other way now. How we simply integrate to go in the reverse order. So sure, if you gave me position, I could figure out velocity and acceleration. But what if you gave me acceleration? Turns out you can still figure out the other two by going back. And with enough information, you can find the exact functions. So, example. This is coming from like physics. The free fall problem. Say,
Physics.
no,
Next term.
acceleration due to gravity is minus 32 feet per second squared, or 9.81 meters per second squared. Negative. It acts downwards. So remember that story when you guys threw me off the cliff?
Yeah.
Oh yeah. Who drove the getaway car again?
I don't remember. I wouldn't trust any of you guys.
Who are you to tell? Your car got up by the pothole. Why?
Find.
Why would we toss him up?
Because we're not going to toss him down if we're standing on the ground. Because then we should be throwing him into the ground. And there's no fun in that.
Quiet down 500 feet. 5 I find Alright, so here we are, we're on a cliff. It's 500 feet high. You threw me off like this, right? Alright, do that. With an upward force that I accelerate and I move at a speed of 10 feet per second in the positive direction first. Eventually, of course, what goes up must go down. Now it turns out, since I don't have like an engine or I don't have an Iron Man suit or anything like that, I won't be accelerating. The only acceleration affecting my body would be gravity. Gravity is eventually going to start pulling me down. So at this point, the only thing I know is my acceleration. Which, since the units are in feet, it will be minus 32. And that's the only thing we know. So now we know we want to go from acceleration to position, so where do we have to go first? Well, we have to stop off at velocity first, right?
Yeah.
Now how do we get to velocity? Find the antiderivative. So this is actually going to be the antiderivative of a of t dt, which is the antiderivative of minus 32 dt. What do I differentiate to get minus 32? Minus 32 t is my variable, right? That's dt plus c. Alright, so this is actually something that gives you my velocity function. But remember I said this could be any constant? It turns out we can find it here. How can we find it? We know some information about the velocity, right? For example, at time equals 0, what is the velocity? It's 10, right? So I get launched off the cliff at 10. So when time starts, the clock starts, I'm moving at 10.
Wait, how do you know it's 10?
Yeah, that's not like absolute zero though. That's like
Absolute 0. This means d of 0 is just minus 32 times 0 plus c. That should be equal to 10. This means that c equals 10. And so my velocity function would be minus 32t plus 10. Right? And now I can go to position. Position is going to be the antiderivative of velocity. What do I differentiate to get minus 32t? Minus 16t squared. Because I do the rule we had over there with this, you add 1 to the power, divide by the new power. So this becomes t squared over 2. The 2 cancels this, you get 16. This guy here is just going to be 10t, and again plus c. Do I have enough information to find the c? Of course. Relaxed. We know the initial position, which is what? 500. And the clock starts, I'm at a height of 500. This means 500 is equal to, when I plug in 0 into this function.
But this is before the game comes up?
This is the instant when you release me. Stop imagining. Like, everyone's getting quiet now because they're just imagining. This is a different C. This is a whole different C. You can call this C1 and C2 if you want. This means that here C is going to be 500. So S of t is going to be minus 16t squared.
So C is like B1 and B2?
This is going to be the position.
It's going to be like a test.
Yes, the question line is guaranteed to come on.
I go to 2 for that. So,
about it.
Makes no sense.
Right now, I haven't got anything in my mind.
I don't know if he came up with Newton.
Newton.
God.